This video is going to introduce you to scatterplots and correlation. A scatterplot is a graphical display of the relationship between two interval variables. It's the last relationship that we haven't taken a look at yet this semester. The response variable is defined to be the variable that gets plotted along the y-axis that we're trying to explain or predict. The predictor variable on a scatterplot is the variable that gets plotted along the x-axis, and we're trying to use that to explain changes or make predictions about the response variable. The observations on a scatterplot get plotted as ordered pairs, with the predictor variable as the x-coordinate and the response variable as the y-coordinate. As an example, suppose we collect GPA and ACT scores from 21 college-bound high school seniors. We want to use their GPA to see how closely we can predict their ACT score. You can see the scatterplot of the results at the bottom. As an example of how to read this plot, this particular point has an x-coordinate of about 3.9 and a y-coordinate of about 29. This means that this person had a GPA of approximately 3.9 and an ACT score of 29. Since ACT score is plotted along the y-axis, it gets treated as the response variable. Similarly, since GPA is along the x-axis, we're using GPA as the predictor variable. Now this is all great, but we actually need a couple of different ways to describe the relationship between these two variables. One method of describing a scatterplot is based on its linearity. On the left, you see two scatterplots where there's a linear relationship between the variables. We could draw a straight line through those scatterplots, and a majority of the points would be relatively close to that line. This is what we strive for in linear regression. On the right, you see two scatterplots where there is not a linear relationship. This is what we would call a nonlinear relationship. Clearly, the plot on the top has a quadratic relationship. There's not a straight line that can be drawn through there that describes what is truly going on between the two variables. And on the bottom, it's very subtle, but you can vaguely see a slightly curved relationship between x and y. A straight line comes close to working, but a slightly curved line works a little bit better, indicating a nonlinear relationship between x and y. The other way that we can describe a scatterplot is based on the direction of the relationship. Basically, two variables have a positive relationship if, as values of the predictor variable increase, the values of the response variable also tend to increase. This is what you see occurring on the left. On the other hand, if the response variable tends to decrease when the predictor variable is increasing, we have a negative relationship between the variables. Taking a look at the scatterplot between GPA and ACT score, what we want to do is identify the characteristics of the scatterplot. The first thing we should do is draw a line through the scatterplot to try to figure out what the relationship looks like. A reasonable guess for the line looks something like this red line. In class, we'll talk about specific ways we can get the best line through the data, but this is a reasonable estimate. Looking at this red line, we can clearly see that there is a linear relationship. Most of the points are relatively close to the line, and it doesn't appear as if there's a curved relationship at all. The other thing that we need to look at is the direction of the relationship. The slope of this red line is positive. As GPA increases, ACT score tends to increase. So we would say that the direction of the relationship between ACT score and GPA is a positive relationship. One numerical measure that we can use is called the covariance. The covariance is a measure of the strength of the linear relationship between two interval variables. Just like the mean and the standard deviation and the variance, we have two different values for the covariance. The population covariance is denoted by the Greek letter sigma, with x and y in the subscript, indicating that we're looking at the relationship between two variables. We also have a sample covariance, denoted by the letter S, with x and y down in the subscript as well. Now, anytime we have a positive covariance, it's an indication that we have a positive relationship between x and y. Similarly, if we have a negative covariance, it's an indication that there is a negative relationship between x and y. If the covariance is equal to 0, this implies that the two variables are not related at all. Now, one problem that we're going to run into is the fact that the covariance is unbounded. The range is technically negative infinity to positive infinity. The reason this is a problem is that it leaves no room for interpretation. If we get a covariance of 200, we have no way of telling if this is a large or a small covariance. We have no way of telling if this is a strong or a weak relationship between our two interval variables. One way to fix this is to look at something called the correlation. The correlation is another measure of the strength of the linear relationship between two interval variables. Just like all of our other numeric measures, we have both a parameter and a statistic that describe the correlation. The population correlation is denoted by the Greek letter rho, while the sample correlation is denoted by the letter r, and it's calculated by taking the sample covariance between x and y, s sub xy, and dividing by the sample standard deviation of the predictor variable, s sub x, times the sample standard deviation of the response variable, s sub y. Just like with the covariance, if we have a positive correlation, we have a positive relationship between the variables. If we have a negative correlation, we have a negative relationship between the variables. The nice thing about the correlation, though, is that it's bounded below by -1 and bounded above by +1. As a result, the correlation has a very clear interpretation that tells us what's going on between our predictor variable and our response variable. Now, this table here divides up the range of possible correlations, -1 to 1, into 7 distinct ranges that tell you what type of relationship exists between x and y. For example, if your correlation lies between 0.7 and +1, we have a strong positive linear relationship. If the correlation is between 0.4 and 0.7, we have a moderate positive linear relationship. A correlation between 0.1 and 0.4 indicates a weak positive linear relationship, and a correlation between -0.1 and +0.1 indicates little to no linear relationship. We have the same types of relationships when we have a negative correlation, only this time they're described as being negative linear relationships. Weak goes from -0.1 to -0.4, moderate goes from -0.4 to -0.7, and strong goes from -0.7 to -1. And so going back to our GPA versus ACT score example, we find that the covariance between the two variables is 1.385. The sample standard deviation of the GPA scores is 0.55, and the sample standard deviation of ACT scores is 5.03. What we want to do first is calculate the sample correlation between GPA and ACT score. The sample correlation is the covariance divided by the product of the individual standard deviations. This gives us 1.385 divided by the quantity 0.55 times 5.03. This works out to 0.5. Another reasonable question to ask then is what type of linear relationship exists according to the correlation. If we take a look at the chart on the previous slide, we'll find that 0.5 lies between 0.4 and 0.7, which is an indication that there is a moderate positive linear relationship between GPA and ACT scores.